Now, there could also be isolated real eigenvalues, and we will see that this thing has a meaning in identification also, but the point is that this eigenvalue, which is complex in general, if we have the complex plane here with the real and the imaginary line, if we get a eigenvalue here, that's complex, then necessarily there must be one here. If I get another one here, then necessarily there must be one here. Now I could get, however, another one that is real, and it would be like that, right? So what does that tell you right away is that if the matrix A is an odd size, 3, 5, 7, 9, etc., it will always have, for sure, at least one real eigenvalue. If the matrix is even, 2, 4, 6, 8, 10, etc., it may or may not have real eigenvalues, because you could have, for example, 1, 2, 3, 4, right? Okay? All right, let's see, what else? Yeah. So let's clarify, not clarify, but just bring out a topic that is sometimes a misconception that people tend to forget. We know that if, let's say, phi was 1, 2, 3, right? Then that means that A times phi was equal to 1, 2, 3 times some scalar, right? Okay, which was the eigenvalue. Now the question is this vector arbitrary to within a scalar? Yes, we know that, right? Everybody knows at this stage of the game that if 1, 2, 3 is the eigenvector, so it's 10, 20, 30, right? And so it's 100, 200, and 300. Because it's obvious that I could multiply both sides of this thing by 10, and I could hide the 10 here, right? And I could hide the 10 here, so that would be 10, 20, 30, and that's no problem. What people sometimes forget, or don't have clear, is that it's not only that scalar, that it's arbitrary, is not necessarily real. So if I have an eigenvector is 1, 2, 3, and I write 1 plus 7i, and 2 plus 14i, and 3 plus 21i, that is also the same eigenvector, right? Which I just multiply times 1.7i, right? So this eigenvector, you might see it like this in an identification, and you might think I got a complex eigenvector. Well, if you'd like, but obviously that eigenvector can be normalized to real without any difficulty, because it's 1 plus 7i, which is just a constant, times 1, 2, 3, right? So it is important to keep in mind that when you see complexity in an eigenvector, you have to remember that there is an arbitrary scaling, and that scalar is whatever you like, and it can be complex too, okay? All right, let's see what else. What else do we need to say here? Okay, we can say that if lambdas are distinct, that is, if they're not repeated, then you are guaranteed to have one eigenvector for each eigenvalue, okay? So if the eigenvalues are distinct, one is sure that there is one eigenvector for each eigenvalue and that these eigenvectors are linearly independent. Right? Now, if they are linearly independent, that means essentially the following, that, and I will go back to what happens when this is not true. That means that if you write this equation, A times phi1, you have something like phi1 times lambda 1. And you can also find that A times phi2 is phi2 times lambda 2, etc. Right? So, if you do that, for all of the phis, because there is one for each eigenvalue, if the matrix is n by n, there will be n of them. And so the set of equations, A times phi1, A times phi2, A times phi3, can be written in terms of A times the matrix that contains all the phis is equal to the same matrix that contains all the phis times a matrix which is diagonal that contains all the lambdas. So this phi is equal to phi1, phi2, etc. in its columns, and this lambda is a matrix that contains lambda 1, lambda 2, etc. in its diagonal. Right? That is true always provided, I repeat, that there is one eigenvector for each eigenvalue. There are some cases where if there are repeated eigenvalues, okay? There are some cases where there are repeated eigenvalues. For example, an eigenvalue might be repeated twice, but there is only one eigenvector. If that happens, then that matrix is referred to as being defective. That is, matrices in which the number of eigenvectors is less than the number of eigenvalues, or which is the same, the number of eigenvectors is less than the size of the matrix, are known as defective. Defective matrices, well, in that case, we can no longer find a set of vectors that are linearly independent and that allow the following. Actually, let me step back. Before I say that, or before I emphasize that, I just want to point this out. If I have this situation like that, because the phis are linearly independent, it allows me to say that this is true. That is, multiplying by the inverse of the mode shapes or of the eigenvectors, we get this. And this is called the spectral decomposition. The spectral decomposition of a matrix means that the matrix can be expressed as a triple product in which the first matrix are the eigenvectors, the second matrix is a diagonal matrix of the eigenvalues, and the third matrix is the inverse of the first matrix. Of course, in order for this to be possible, which is what should have been the order I used, in order for this to be possible, the eigenvectors or this matrix must have an inverse, which means its columns must be linearly independent, and this decomposition requires not valid if matrix A is defective. In that case, we have to use something called a Jordan form. In the defective case, we have the Jordan form. Okay? In the defective case, we have the Jordan form. Now, defective matrices require that there be repeated eigenvalues. Now, here, to be clear, The fact that there are repeated eigenvalues does not mean that the matrix is defective. However, if the matrix is defective, it needs to have repeated eigenvalues. Okay? To give you an idea of a matrix or of a situation of repeated eigenvalues, at least in theory, is the case of a structure that is symmetrical. So if you think about having a building in which, you know, the north-south and the east-west properties are the same, right? 4 columns that are the same, 4 beams that are the same, etc., whatever, right? Then obviously the frequencies in this direction are the same as the frequencies in this direction, in theory, right? And therefore you have repeated eigenvalues, and it's clear that in that case you do have the mode shape this way and you do have the mode shapes this way. Now, one thing that this brings to mind, and I discussed in the class a little bit yesterday, is that repeated eigenvalues are really a theoretical construction, because in reality they are an impossibility. For example, if you try to build this structure and you say that it has identical properties this way, it's not really possible to do that, right? So no matter how hard you try to make the properties in these 2 directions to be the same, it doesn't turn out to be the same. So when we say mathematically that 2 eigenvalues are the same, remember that that means that they are the same with infinite digits, right? 3.12579243457 etc. has to be the same as the other one. And it's clear that if one pebble was in the wrong position or in a different position this way or that way, they are no longer the same. So repeated eigenvalues are kind of a mathematical construct. In practice, what we have is eigenvalues that are very, very close. Now, when eigenvalues that are very, very close are present, a number of issues arise, and we will discuss those issues, which is important to be aware of when we get to that point in the class. At this point, we just simply say, for your general background, that when eigenvalues very close, one of the things that happen is that results that are normally anticipated start changing, and you're wondering why. It may even appear that your identification results are wrong, but they may not be wrong, they may be perfectly fine, and it's just the fact that you have 2 eigenvalues that are very close. The reason, well, not the reason, the point is that when eigenvalues get very close, the derivative of the eigenvalues with respect to parameters of the system become very high. In other words, a parameter change on a very small amount can produce a large change in the eigenvalue. Another thing that can happen is that mode shapes, which are normally almost real independently of the damping, when 2 eigenvalues are very close, can become notably complex, even though the damping is very small. And when I say notably complex, I don't mean that, like the example I was making, that you can take a scalar out. I mean that when you plot, in other words, typically, I'm getting ahead of myself, but anyway, typically we would say that if I have, let's say, this 1, 2, 3, 4 story structure, you know, in any given mode, the amplitudes may be like this. So this is, let's say, first floor, second floor, third floor, fourth floor. Notice that I didn't do them real. All I mean, because this normalization is arbitrary, what I mean is that they are essentially aligned. They're either one way or the other, right? Now, that means that this mode shape is essentially real. That angle, maybe it's not very clear in the drawing, when you see the play, so I'll exaggerate a little bit. But what I mean is that these lines, which are the amplitudes of these things during vibration, have angles that are, you know, very close to some line. Now, when the two eigenvalues are very close, you might find that the situation might be like this. Okay? Floor 1, floor 2, floor 3, floor 4. So the mode shape looks extremely complex, even though the damping was very small. Okay? Oftentimes people think, oh, I did something with wrong with my identification result because I get this crazy looking mode shape at the coordinates that I'm measuring, and I really have low damping. But it may be, as I say, that there's no problem, there's no error. It's just that you have a situation where two eigenvalues, or the mode shape that you're looking at, for example, corresponds to this pole, and there is another pole that is right here. So you have these two very closely spaced poles, and then that creates the issue, right? Closely spaced poles can create this kind of behavior. All right, let me see. I think that, okay, just a few more things to clear up, and on this sort of initial introduction of things. And one, again, this could be part of the jargon, but the term is similarity. Of course, in English, the word similarity has a specific meaning in common language. It means these two things are close to each other, or they look alike, or something like that. Well, in the case of matrices, two matrices, when you look at them, they may have nothing to do with each other when you look at them. I mean, the numbers have nothing to do with each other, but their matrices may still be called similar. And so, why? The idea is that it is a precise mathematical description, and the description is the following. A and B are similar if W times A times W to the minus 1 is equal to B for some W. Okay? In other words, if you can go from one matrix to the other by multiplying by some matrix and its inverse, then those two matrices are similar. Now, why is it that similarity is such an important thing? Well, because all matrices that are similar have the same eigenvalues. Okay? So if two matrices are similar, the numbers may look completely different, but those two matrices have exactly the same eigenvalues. Notice that we've already seen an example of similarity. In fact, when we looked at the spectral decomposition a little while ago, we said that it was like this, right? So you can see that what we're saying is that A and lambda are similar, and therefore have the same eigenvalues. In this case, it's kind of like a circular thing, right? Because the eigenvalues of A are lambda, and the eigenvalues of lambda are lambda because lambda is just a diagonal, and the eigenvalues of a diagonal is the diagonal. So here we can see the very statement that we made here. In identification, this is extremely important because as we will see, depending on algorithms and depending on users' choices and depending on several things, you and I and the next guy may actually obtain matrices when we do something that look entirely different. However, these matrices are, if we didn't make an error, typically, not typically, this matrix are, if they are the system matrices, similar matrices. So when we calculate the eigenvalues of our results, we find that our eigenvalues are the same, even though our matrices look very different. Okay? Now, it is important to also know that all similar matrices have the same eigenvalues, but not all matrices that have the same eigenvalues are similar. Okay? I repeat, all similar matrices have the same eigenvalues, but not all matrices that have the same eigenvalues are similar. For example, if I take the matrix A to be the identity, and I take the matrix B to be this, for example, I can see right away that these two matrices have the same eigenvalues. Why is that? Because in matrices that are because a diagonal matrix, its eigenvalues is just the diagonal. So the eigenvalues of this matrix are 1 and 1. And for matrices that are upper or lower triangular, that is still true. And therefore the eigenvalues of B are also 1 and 1. However, it is not true that I can go from A to B with a similarity, because any similarity that applies to A, given that A is the identity, just yields the identity, right? So no matter what W I choose and I apply it to A, I just get the identity, which is not equal to B, right? So the matrices A and B have the same eigenvalues, but they are not similar. Okay? All right, so we now reach, in this kind of quick, shortened version of our first lecture, we reached the last topic that I mentioned yesterday, which was just the beginning, because we have much more to say, of the singular value decomposition. Now, any matrix that is square and is non-defective has a spectral decomposition in terms of its eigenvectors and its eigenvalues, as we showed. But for a rectangular matrix, Q, we can always find that has R rows and C columns. We can always find the decomposition, which is U times sigma times VT, and I'll explain the T in a second. That gives the matrix Q, okay? This is what we refer to as the singular